The ANGSA initiative, carried out by 90 to 100 scientists and engineers and focused on unopened Apollo 17 samples, have provided many exciting scientific observations about the moon and numerous results that are very applicable to Artemis. Today, I will focus on one very, very tiny aspect, a small aspect of the ANGSA science, and that's essentially using ANGSA and ANGSA samples to examine lunar pyroclastic volcanism, primarily focusing on the volcanism associated with the Taurus Littrow Valley. Next slide illustrates the distribution. Next slide illustrates the distribution of pyroclastic deposits on the moon. This will be in this year's New Views of the Moon 2, and it's initially produced by the USGS. And as you can see here, there are numerous pyroclastic deposits all over the moon. I think over 100 have been documented, and these really represent the transport of volatiles and often near primary melts from the lunar mantle to the lunar surface. The next slide, and while volcanic, and one of the remnants of this type of magmatism are these volcanic beads that occur in all of the Apollo sample suites and the Luna sample suite. And perhaps the best sampling of these pyroclastic deposits is at Station 4 in the Taurus Littrow Valley, often referred to as the Shorty Crater Stop. And I just want to note that these represent high titanium basalts. And the chart that you see in front of you, the one to the left, is just Shorty Crater with some geology put into it from my co-author Jack Schmidt. These do represent the core. The core taken here is 72 centimeters long, and the stratigraphy has been well defined, with the upper portion of the core primarily being orange glass, and the lower part of the core primarily being black volcanic beads. You can see example in the lower right-hand BSE image. And the differences in this stratigraphy is thought to represent differences in volcanic eruptive style. The next chart as part of the ANGSA initiative, Sunadal documented the spectra of black glass beads in the Station 3, not the Station 4, the Station 3 drive tube, which was the focus of the ANGSA initiative, and identified from that spectra the distribution of black volcanic glass in the Taurus Littrow Valley. And that's on the image shown to your right, which shows the variation within the Taurus Littrow Valley and the areas surrounding the Taurus Littrow Valley. And our question is, based on the data we received or the samples from Station 3, does Station 3 double drive tube sample remnants of the pyroclastic deposit not previously sampled? As you can see, there's quite a bit of a distribution. And because the sample was preserved in a core sample vacuum container, is the volatile component better preserved in these particular samples? The next slide just again illustrates the location of the Station 3 double drive tube 73001, which penetrates a light mantle deposit, which is a landslide deposit coming off the South Massif. So it represents material from the South Massif and also material within the valley floor. This also just illustrates the relative location of the Station 3 with the Station 4 Shorty Crater. And you get two perspectives from both of these images. The next slide just outlines at least some of the analytical approaches that we utilized for preparation and examining the samples and the pyroclastic volcanic beads from these samples. Next chart. One of the approaches that we use is we sieve these samples. As you can see, this is an image from Michael Cato, one of our graduate students who did some of the sieving of the regolith from different depth horizons. And we plucked out some of these pyroclastic beads. And this just shows some of the textural variation we saw in the sieve samples, ranging from being fairly glassy, the upper left-hand corner, to and being orange in color, to on the bottom BSE image, you can see there is individual olivine grains within this bead, in addition to skeletal ilmenite. Again, this may be a product of cooling rate that we see in these high titanium volcanics. Next chart just illustrates that in addition to the volcanic beads being within individual lithic fragments, and could you click the slide again to see the video? They also occur within these lithic fragments. And these lithic fragments, some of them, the regolith breccias, can contain only one or two of these pyroclastic beads. But in this case, in class 226, you can see that the whole breccia, regolith breccia, is made up of these beads. And in the beads, and then there's also, as you can see, these little fragments of high titanium basalt that show up here and there on the XCT image. So these are the kind of the samples we are starting to work on to look at these, what information these beads provide us. The next chart just illustrates some of the different textures observed in these volcanic beads, ranging from orange glass on the upper left-hand corner through lithic or glass or beads that are primarily glass but have small olivine growths that you can see growing from the outer portion of the upper part of the bead in the upper right-hand side, to fairly complex crystallization assemblages that you can see in the bottom right-hand corner that is in this image. In the sequence that we looked at, they contain olivines that crystallize prior to fragmentation, and therefore some care must be taken in the selection of olivines or determine the volatiles from melt inclusions. Next chart. The next chart just illustrates some of the characteristics of these beads that we utilize to compare to 74001. And we looked at things such as the percent beads intact, the percent glass, percent volatiles, and the component and the compound beads that we can particularly find. We did find differences between 73001 with regards to crystallization history. Compound beads were very small, and the glass beads were primarily pretty broken up. The next slide just shows olivine morphology and olivine composition, which appears to be related to the morphology of the olivine. And this agrees with some of the work that Heiken and McKay did on 74001. Next chart is kind of a unique basalt, which has textures fairly similar to the pyroclastic beads, but but again, fairly different. The olivine composition is fairly magnesium rich, unlike any basalt from the moon that I've seen. The ground mass shown here is olivine plus plagioclase, which is again is different from any basalt that I've seen on the moon. And the nickel in the olivine, based on our preliminary microprobe analyses, suggests it is fairly enriched in nickel, which is different from, again, most of the Mare basalts and Crete magnesium sweet rocks. Next chart illustrates
10 minutes wrap up time.
What's that?
Sorry, it's been 10 minutes. You didn't hear me at 8.
Okay, I did. Okay. Let me go ahead and go to conclusions, if that's okay. And I'll let everybody just read the conclusions in terms of what some of the highlights are from this presentation. And thank you very much. And sorry that I had to skip over the previous slide. Thank you.